Hello. This is video number 43. And so far, we have looked at graphs some, but it's all been fairly abstract and general. And you could do it this way, you could do it that way, or whatever, but we haven't used them for anything. Let's look at a specific graph algorithm, shall we? I'll phrase this in the form of a question. How can we find the shortest path from some start node, I'll put in parentheses, so we start by picking a start. We pick some particular node in the graph, and we want to find the shortest path from that start node to every other node in a weighted directed graph. Every other node in a weighted directed graph. Whoops, yeah, that was right. Well, I would say we start by trying to get our minds around the question that's being asked here. The shortest path, remember, a path is where you start at one node and then you follow arcs. In a directed graph, we're going to have to be careful with the arrows. They're directional. We can go this way, that way. I don't have any idea where my glasses are. Oh well, I'll do this one blind. I got to have my glasses off to read my notes anyway. I bet I left them outside. Okay, how do we find the shortest path from some start node? And it turns out that it's just as efficient in terms of the order of magnitude to go ahead and find the distance to every other node in the graph, in the weighted directed graph, than it is to find it to one particular node. So we'll go for broke right off the bat. Weighted means that there are labels on the arcs, and for this application, we're going to have some restrictive assumptions about those weights. They've got to be positive numbers. You know, it could be miles, it could be dollars, it could be something like that. But they are numbers, and they can't be negative. If they were negative, then we could oscillate back and forth between two negative numbers and get a smaller and smaller and smaller and smaller distance. But that's no fair. So it's got to be a positive number, strictly positive, not even zero. And directed means that the arcs only go one way. So yeah, this is a pretty specific algorithm. An observation, though, before I even start on an answer, if you think, well, this is so restrictive that it's got to be of limited use, actually, this algorithm has a lot of use. If we can do this, then we can also do a couple of things. We can also do an unweighted graph. How so? If we know how to do this, if we know how to solve this problem, finding the shortest path in a weighted directed graph from one node to every other node in the graph, we could do that for an unweighted graph. Just set the weights to 1. Set each weight to 1. And voila. What you'll end up with is an algorithm that finds the count of the number of arcs, because there's no weights to pay any attention to. But we could still apply this algorithm to an unweighted graph. We could also apply it to an undirected graph. Which you will recall a strange thing. An undirected graph is actually a special case of a directed graph. Put backwards arcs for each, put in backwards arcs. Let me say it first and then see if I can write it. What we're going to need to do is put in a backwards arc for every forward arc. And if we do that, then we can go two directions on each one of the old arcs by having an undirected representation of the same graph. In other words, if we've got an arc of 5 from A to B, we'll just put in an additional arc of 5 from B to A. See how that works? Undirected graph. What was I going to say with but? Oh. How about just put? Put, well, I'll put in quotes. I don't know if this is a technical term. Backward arcs in the graph for each forward arc. It seemed like a painful little observation here, but it's worthwhile. It's saying that even though the original problem is framed as for a weighted directed graph, if we solve it for a weighted directed graph, then we've also got it for unweighted graphs. We've also got it for undirected graphs. So there we go. I'm going to start small down here with the answer. And by small, I mean a small graph. Here's an example. Node A. And that'll be my start node. And let's see. I'm going to back up so I've got room to make a bigger graph. Example. A. And A goes to B with the, well, no, B's over here. I'm going to try to match my picture so I don't confuse myself. B is distance or cost or whatever, 50 away from A. 50 units, 50 generic units away from A. With 100 units, a distance of 100, I could go to node C, and 30, I can go from C to B. There. First of all, does that fit the bill? Yes. It's a weighted graph because there are numbers, labels, non-negative, and what else? It's a directed graph because there are arrowheads on each one of the arcs. So that is one that we can work with for an example. Let's find the, what are we looking for? The shortest path, the distances. A to A. Well, we don't have to go anywhere. The distance from A to A is 0. That one's done. What about A to B? Now, we're looking for the shortest path. Well, the shortest path is that 50. It's either that or the 130, so let's take the 50. A to B is 50. And the shortest distance from A to C. C is pretty far away. It's 100 over here. But that's the only way to get there. So the shortest distance from A to C is 100. Well, that was easy, wasn't it? Oh no, wait a minute. After all that claiming that I was going to stick to what was on my paper, whoops. Here's a whoops in hot pink. What if A to C, the arc that goes from A to, no, not from A to C, A to B, I mislabeled that, is 500, not 50. I did a different color so it show up. I copied my graph wrong. Oh, silly me. So A to B is not 50, it's 500. Does that change anything? Well, let's see. A to A is still 0. You don't have to go anywhere to get from A to A. A to B, that is going to be different now. Look at this. It's not 500. That's not the shortest path from A to B. And A to C, that's not going to change. So that one's okay. A to B is going to change, though. A to B, the shortest distance is now 130. It's not 50. And a tiny little example, but still we can make a big observation. In a weighted directed graph, it's not a count of the arcs. It's a total weight of the arcs to get there. So even though B is adjacent to A, I can get there following one arc. 500 is absolutely not the shortest path. Even got to update my original wrong answer over here. 500 is not the shortest path from A to B. It's shorter to take more arcs. Maybe it's cheaper to take a connecting flight than it is to take your direct flight. There, a real-life metaphor. Man, I wish I knew where my glasses were. That's going to bother me now. I'll try not to be distracted. I must be distracted, though, because I'm making all these boo-boos. Double whoops. H. Can't even spell whoops. Thanks, 2020. Double whoops. I forgot what? I forgot D. Forgot no D. ABC, here's D. And maybe we got an arc from A to D that's weight 40. And an arc from D to C that's weight 10. Well, it's a different color, but And we've got an additional node to figure out now. Now we've got to figure out the shortest distance from A to D. So it looks like the shortest distance from A to D is going to be 40, because that's the only way we can get there. But you know what? We need to start all over again. Look at this. If we start at A and go to A, that's never going to change. A to A, since that's the start node, that's always going to be 0. Now then, do we know the shortest distance from A to C at this point? It turns out, even though C is adjacent to A, we don't know. We don't know the shortest distance. Here's what we can do, though. The distance from A to A is absolutely positively 0. I'm going to get serious, back in black. If I can find my black, that's black. And I'm going to put a distance of 0 on A, and now pronounce that done. That part of the problem is solved. I do know the shortest distance from A to A. Okay, now do I know the shortest distance to anybody else? Well, that's a 500. It looks like a 50 with a straight 0, but that's a 500 now. That's a 100, and that's a 40. I do, in fact. I jumped the gun, but I do know the shortest distance from A to D. And you might think, well, you know what? Dr. England, he's acting like he's being all funny and everything, but he might have 30 nodes in this graph before he's done. He might keep adding stuff. I might very well. But let's say that these are the only 3 nodes, B, C, and D, the only 3 nodes in A's adjacency list, period. I hereby swear that I shall not add any more arcs that are directly adjacent to A. Now then, can I answer the question, do I for a fact, now that he's leaving it alone, do I for a fact know the shortest distance between A and any other node in the graph? The answer is yes. It's still A to D. Why? Here's a couple of reasons. Well, 40 is less than 100. 40 is less than 50. That's part of one reason. Here it is. If, think about this real hard. This is kind of a theoretical part that actually goes beyond the scope of this graph. I'm going to start again. Listen. If there were a shorter path from A to D that involved multiple stops along the way, no direct flight, it would have to go through one of the other nodes that's adjacent to A. Let me say that again. If there is some unknown path out here in this graph that Dr. England's going to make up of 30 nodes, if these are the only 3 nodes that are adjacent to A, then I can pick 40 and know for a fact that I can freeze this distance of 40 at node D, and it shall not be updated with a smaller number later. Why? Because if there were a shorter path that went through other nodes, it would have to either go through C, which is 100 away, that's further than 40, or it would have to go through B, that's 500 away, that is certainly more than 40. So I know for a fact that the shortest path from A to D is in fact the 40. That's the only one. That's the reason I'm making a big deal out of that. I'll double circle these. I know about you, and I now know about you. Those are not going to be updated. They can't be. Because any shorter path to D would have to either come through C, come through B, and I've already told you about that. Those are already further away than D. Now, now I need to expand my horizons. Now, I not only want to look and see who's the closest directly to A, I want to see if I can make a stop in city D over here and get to some of the other nodes more shortly, more quickly. So far, I'll put the distances I know about so far. So far, the best distance I know about to B is 500. That's a tiny little 500 there, but that's a big number. The shortest path I know about so far from A to C is 100. Also a big number written small. And this is a tiny little graph. I don't know if it can bear all the weight. See what I did there? Okay, so this is 500 away, this is 100 away. Oh no, do I know of any shorter path? Now I expand my horizons and look and see what nodes I can reach from D. How cheaply is it to stop in Dallas before I continue on my journey? Well, look at this. From A to D was 40. The additional hop from D to C is only 10. So I already know about a shorter path to C than the 100 just by going through D. See what happened there? I'll repeat that. Don't just look and see the shortest one from A, the next one would be C, because that's only 100 away. And 40, I already know about that. I've already frozen that. We're not going to update D anymore. But we might update these down here. Those are still in limbo. And look and see what happened. 40 over to D, 10 more down to C. I cross out the tiny 100 and I'm going to have to put a tiny 50 in its place. That was only a coincidence. That has no relationship to the original distance A to B, and I'm sorry about that. I didn't realize it, or I would have changed my example. Back up. Okay, A to D is 40. The additional distance from D to C is 10. So I know 50 exists as a path. It might still be updated later. I don't know. But now that I've updated that, the shortest known distance to C is length 50. The shortest known distance to B is length 500. At this point, for the next iteration, iteration? Yeah, this is an iterative algorithm. It's not recursive. Phew, we've left recursion behind, at least for now. From A to C, I know a shorter path from A to C. A to C, shining C, is 50. And I know I'm not going to improve on that. Why not? Because if there were a shorter path to C, it would have to come through some other node. These are the only two nodes that I know for sure their shortest distance to A. So whoever is closest to either A or D now is the new one to join the shortest path club down here. That was the smallest unfrozen distance when I updated it from, well, first of all, I updated it from 100 to 50. But now at 50, it is closer to A than anything else in the graph. The only other candidate is B, and that's not even close. That's 500. So I'm going to officially freeze C and say I now know the shortest distance to you. I'm very abstractly, perhaps not terribly well, but I'm verbally tracing through the algorithm that we would actually have to construct that's going to do this. Now then, who's unknown? Well, A to D, I know the shortest distance there, I froze it, and that's what the double circle in the box on the number means. A to C, I know that shortest distance, 50. Who's left? The only unfrozen node at this point is B. So let's see if I can update anything from A. There's nobody else from A that I can offer a better distance to. There's nobody else from D I can offer a better distance to. But now C's joined the club. Is there anybody I can get to from C and offer them a better, shorter distance than they know about already? Well, let's see. My distance from A is 50. So if I use myself as a starting point, I'm 50 away from the start. I can go an additional 30 and get to B. Think about that real hard. Now that we've frozen C, C is going to go looking at all the unfrozen nodes. Can I help you? Can I help you? Can I offer you a shorter distance than you know about already? And yes, it can. C is frozen at distance 50, known for a fact. Once we froze, we never look at it again. We know your shortest distance. Can I offer you a distance of 50 plus 30, also known as 80? Node B over here. And B is going to eat that up. 80 is much less than 500. So it updates the node's distance field. If we get vulgar and start talking about actual structures and fields and stuff, the distance field inside B will now update from 500 to the much more tempting 80. Yeah, I like that distance a lot better. And that's all the updating that we can do. Then we go shopping. What's the shortest distance? What's the smallest distance? The closest node, in other words. What's the closest one to A that hasn't been frozen yet? Well, in this case, we don't have a lot of options. The closest node to A that hasn't been frozen is the only node that hasn't been frozen. And just in the nick of time, its distance got updated to 80. And now we will update A all the way to B. We freeze you at distance 80, and that's it. The distance from A to B is 80. And check, please. That's it. That's the best we can do. Now that actually has, for this tiny little graph, and this tiny little set of arcs, and the tiny little distances we're talking about, oh my goodness gracious, that has a lot of stuff packed into it. What do we know and when do we know it? That's a question to keep asking at every step. Well, at the very beginning, we don't know much at all. We know the distance from A to A is 0, and that's our starting point. And then the iteration begins. As we freeze a node, I know your shortest distance. I'm never going to look at your distance again because I know that's the best I can do. We start off, the only node like that is A. A looks around at all of its adjacent nodes. Maybe go through an adjacency list. oh, that's getting vulgar again. That's perilously close to actual code or even pseudocode. Let's just look at the graph. Can I offer you a distance of 40? No, D. Yes, I'll take that. I'll be 40. How about you? C, I'll offer you a distance of 100. Well, that's better than the infinite distance that I assume I'm away so far. So yeah, I'm going to take the 100. And even B will accept the distance of 500. Yeah, that's the best known distance from A so far. But that doesn't mean that it's permanently going to be 100 and permanently be 500. It means that now I do have better distances. Those might eventually be frozen, but it also means that those could be updated later by shorter paths that go through other nodes. What other nodes? We freeze them one at a time, one baby step at a time, as we step on the stones across the stream. We find the closest unfrozen node and freeze it. And I've already gone through the argument of why we know that's the best. The closest unfrozen node to A in the first iteration is D, 40 away. We know that's the best distance because any shorter path would have to be going through B, which is at least length 500, or going through C, which is at least length 100. So 40 is the best we're going to do for D. And then here comes if there is a confusing part, it's this. Once we freeze a node, we look at all of the nodes that are adjacent to either one of these. We look at all the nodes that are adjacent to A and adjacent to D to find an unfrozen node to see if there's any distances that we can update. In fact, there was here. From D to C, we could update that from the 100 it knew about to the distance to D plus the additional 10 more. That got updated to 50. I think I'm in an iterative loop, if not an infinite iterative loop. That is quite an example. Actually got a lot of mileage out of that for being such a tiny example. But that'll do for now. As I said, this video has a lot crammed into it. You might want to watch this one twice, whether you ever watch any of them twice, or at least once all the way through. I'll see you online.